Let me start with a question. What is this repository doing that's so unusual?
It's running a 2.78 trillion parameter language model on a single CPU, using just 8.24 GB of RAM. No GPU, no deep learning framework, no BLAS. It's all written in portable C99.
Wait, a 2.78 trillion parameter model? That's bigger than most of the largest models in existence. How is that possible on a CPU?
The key is quantization and memory efficiency. The model is stored in a compressed format called MXF-FIR, which allows it to fit into memory. It's also optimized to stream parts of the model from disk as needed, rather than loading everything at once.
So this is a full inference engine for a massive language model. What makes this approach different from typical deep learning frameworks?
Typically, you'd need a GPU and a framework like PyTorch or TensorFlow. This repo is self-contained, with no dependencies. It's written in C99, which means it's portable across different systems. It also avoids the overhead of frameworks by implementing everything from scratch.
But why would someone want to run such a large model on a CPU instead of a GPU?
For portability, this code runs on any system with a modern CPU and enough RAM. It doesn't require specialized hardware. It also has a very small memory footprint, which makes it suitable for deployment on systems with limited resources.
The README mentions a mixture of experts approach. Can you explain what that means in the context of this project?
The model is structured as a mixture of experts, which means it has many submodels that can be activated based on the input. This allows the model to adapt its behavior dynamically while keeping the overall size manageable. It's a way to scale the model's capabilities without increasing the number of parameters directly.
I see. The repository uses linear attention. What's the significance of that?
Linear attention is an alternative to the standard attention mechanism in transformers. Instead of requiring quadratic memory with respect to the sequence length, it scales linearly. This is critical for handling long sequences efficiently, especially since the model is running on a CPU and can't rely on GPU acceleration for memory-heavy operations.
So the model is designed to be memory efficient. What specific techniques are used to achieve that?
A few things. First, the model uses quantization to reduce the precision of the weights and activations. This cuts down on memory usage and computational requirements. Second, it streams parts of the model from disk as needed, rather than loading everything into memory up front. This is called memory streaming and is a key optimization for keeping the memory footprint low.
I noticed the repository includes benchmarking data. What's the performance like on different systems?
The performance varies based on the available memory. On an 8 GB system, it takes about 26.5 seconds per token. If you have more memory, like 128 GB or more, it can fit the entire model in memory, which dramatically reduces the time per token to about 5.6 seconds. But the output is byte identical across all systems, only the speed changes.
So the output doesn't change with more memory, only the speed. That's a big deal. Why is that possible?
Because the model is deterministic once the input is fixed. Even when parts of the model are streamed from disk, the same calculations are performed in the same order. The only difference is how long it takes to get the result. That's a major advantage for consistency in inference.
What about the limitations of this approach? Are there any caveats?
Yes, for one, the model is not optimized for real-time performance. It's designed for accuracy and portability, not speed. Also, the implementation is in C99, which is a very old standard. This means it can't take advantage of newer compiler optimizations or hardware features available in more modern C standards.
So this is a full-featured, portable, and memory-efficient implementation of a large language model. Who would actually care about this?
Engineers and researchers who want to experiment with large models on commodity hardware. It's also useful for deploying models in environments where GPU access is limited or where portability is a priority.
One last thing, how does the project ensure correctness when porting from PyTorch?
They have a two-tier validation strategy. First, they re-implemented the same math in pure PyTorch as a reference. Then they validate the C implementation against that. This allows them to catch bugs early and ensures that the C code behaves the same way as the PyTorch version, even if it's written differently.
That's impressive. Any final thoughts on the impact of this project?
This project shows that it's possible to run extremely large language models on commodity hardware. It's a demonstration of what's possible when you focus on memory efficiency, portability, and correctness.
And that's a big deal. Thanks for walking through this codebase.